Hi everybody, it's Jessidens here, and I'd like to give you a quick demonstration of the new Boldport Capaci-Meter. I've designed an enclosure for this which I've 3D printed, so in there is the battery and also a switch, so that's a nice neat way of holding the capacimeter. If you do want the STL files for that, take a look at the capacimeter channel on Discord. If you can't find them there, drop me a line on Discord and I'll point you in the right direction. So I've got a couple of capacitors that I'd like to demonstrate on the capacimeter that have some interesting characteristics. Both capacitors are 4.7 nanofarad capacitors, and this one is out of a Velleman selection box. So it's a cheap box full of lots of different value capacitors, and I'm going to put that on the test probes, which I've got plugged into 2mm holes on the printed circuit board, so ideal for test leads. So we can see here with this capacitor under test, we're reading 4.1 nanofarads, so we're currently on the 9.9 nanofarad range, and in fact this capacitor has a very large temperature coefficient, so we can see already after handling the capacitor the capacitance has dropped by a little bit, now 4.0 nanofarads. If I warm the capacitor up with my fingers, we can see the capacitance rise very slightly there, so 4.1, may even go up a little bit further. The capacitance is very dependent on the temperature, and in fact if I use a freezer spray on this capacitor, we can see the capacitance change by a very large amount. So there's some freezer spray on there, some frost is already appearing on that capacitor, and we've gone down to about 0.5, 0.6 nanofarads, 0.9, now it's up to 1 nanofarad. So the capacitance actually dropped to about 10% of its nominal value when freezing, and as the capacitor is warming up, the capacitance is recovering back to, well, close to its original value. We're now about 3.2 nanofarads, 3.3, and if I put my finger on there we can speed up the warming process there while we're 4.1 nanofarads. So a very large temperature coefficient on that capacitor. That capacitor itself is a very poor performance dielectric type called Y5V. So they're very well known for having a very wide temperature coefficient. So don't use cheap ceramics for any application that requires any degree of stability at all. So if we now change the capacitor to this capacitor, which is from Farnell, this is made by Vichy and has an COG or COG dielectric, much more stable dielectric, and we can see the capacitance there is showing very close to what it should be, 4.7, so 4.7 nanofarads. And if we use the freezer spray treatment again on that capacitor, we can see it's gone frosty almost straight away. The capacitor's gone frosty, and the capacitance is remaining very stable at 4.7 nanofarads. So quite an interesting comparison between two types of capacitor. One of course is a very cheap capacitor, and this particular one from Vichy that I bought from Farnell is a lot more expensive, but even so, in the grand scheme of things, it's not a lot of money. It's probably about 20 pence, something like that, as opposed to 1 or 2 pence for the much cheaper capacitors. So it gives you a good idea of the sorts of performance differences you can see between cheap and not so cheap capacitors. So it's always worth checking the dielectric type. So the good one in this case is a COG dielectric, sometimes known as an NPO dielectric. So I hope you found that interesting, and I shall speak to you again soon.